Power's not, but I am. When we left off, we were talking about this series, 1 over x squared plus 7. And here are the terms. Notice how it's not like a straight line or anything. That's worth pointing out. It's not like a perfect exponential function or something like that. But what's important to us is that at every step of the way, it is all these green dots, which are 1 over x squared plus 7, are always smaller than 1 over x squared. We use the term bounded below. 1 over x squared, bounded above. 1 over x squared plus 7 is bounded above by 1 over n squared. And since 1 over n squared converges, and 1 over n squared plus 7 is smaller than 1 over n squared, 1 over n squared plus 7 must converge also. So that's the phrasing we would use. Since 1 over n squared plus 7 is smaller than 1 over n squared for large n's, and 1 over n squared converges because it is a p-series with a p of greater than 1, 1 over n squared plus 7 must also converge. Notice this is only because 1 over n squared plus 7 is always a little bit less than 1 over n squared. If 1 over n squared plus 7 was a little bit bigger than 1 over n squared, say, for example, if it was 1 over n squared minus 7, we replace this with a minus sign, and now we've got a slight problem. We can ignore the lower values for n. We've got a slight problem that 1 over n squared plus 7, all of these green dots, they're always a little bit bigger than the red dots. So the direct comparison test doesn't work anymore. The other half of this is that, which by the way, that doesn't prove that 1 over n squared minus 7 diverges. It just doesn't prove that it converges. Okay, the flip side of that is if we have a series that is always a little bit bigger than, in other words, a series that is bounded below by a series that we know diverges, then the series that is a little bit bigger, whose terms are always a little bit bigger than a series that diverges, must also diverge. So the example here is 1 over ln of n. If we look at 1 over ln, and so we compare 1 over ln of x, compare that to 1 over x, well, since the ln of x, once x gets, past a certain number, which is not very big, ln of x is always smaller than x, which means 1 over ln of x is bigger than 1 over x. And we know that 1 over x diverges, so 1 over ln of x must also diverge. Since 1 over the ln of n is bigger than 1 over n, and 1 over n diverges, 1 over ln of n diverges also by the direct comparison. So that's the direct comparison test. The problem with the direct comparison test is what I alluded to before. Well, what about 1 over n squared minus 7, which is always a little bit bigger than 1 over n squared, but come on, it's barely bigger, right? Like, does it really matter that it's a little bit bigger than 1 over n squared minus 7? Could that really make a difference? The answer is no, it doesn't make a difference. But we need another test for that. And this is the one that's much more complicated in language, but it's not that much more complicated in ideas. So try not to be confused by the language on the screen. We have something called a limit comparison test. By the way, this is only for series with positive terms. It doesn't work for alternating series. To find out if a series converges, we're going to compare it to another series that, hopefully we already know if it converges or not. If the limit of the ratio of f of n over g of n, so that's the ratio, that's the limit that we're going to talk about. if I were to write it out in handwriting, it would look a little bit nicer. The limit as n approaches infinity of f of n over g of n. If that limit is a positive real number, which can only happen if f and g are of the same order, like if they're both polynomials of the same degree, or if they're both exponential, or if they're both factorials, something like that, then they either both converge or both diverge. So here's an example that is very similar to the one I just mentioned before, the one that gave us this problem. 1 over n cubed minus 11, it's like, well, we should be able to compare that to just regular 1 over n cubed, which we know converges. But the problem is that 1 over n cubed minus 11, the red one is 1 over n cubed. Our green one, it's bigger. Well, you can't prove that a series converges if it's bigger than another series that converges with the direct comparison test. But with the limit comparison test, we can. So the way it works is we just say, we just give them names so we don't have to write the whole thing over again. It's a little bit easier this way. If we just say let f of n equals 1 over n cubed minus 11, g of n equals 1 over n cubed. And so the limit as n approaches infinity of f of n over g of n equals 1. Because as n gets bigger and bigger and bigger, the minus 11 matters less and less and less to me. Basically, 1 over a billion cubed and 1 over a billion cubed minus 11 are pretty much 1 because they're pretty much the same number. Since we know g of n converges by the p-series test, f of n converges too. It should sound very similar to the direct comparison test because it's almost the same idea. It's just technically the direct comparison test doesn't apply because this series is just like a little bit above the converging p-series that we know about. But by the limit comparison test, we can say that it works. On the other hand, if L is equal to 0, which can only happen if f is a lower order, basically that means a smaller degree, than g of n, then if L is smaller than g and g converges, so does f. The order here, like the order of size, we have a power series, like a p-series, like n squared, n cubed, n to the fourth, is smaller than an exponential, like 2 to the n, or 3 to the n, which is smaller than a factorial.